with undergraduates in Costa Rica on a project that uses geoscience to investigate the origins, the current state, and the potential pathways of the Cordillera-Talamanca mountain range in southern Costa Rica. In 2017, he published an article about the discovery of enormous mass of warm rock rising beneath New England. And he's going to talk more about that in his presentation, I hope, because I'm curious too. And the title of his talk is Science in the Public Eye: How a Study of the Physical Properties of the Earth Becomes a Threat of Volcanic Catastrophe.
Okay.
So over to you.
Two things before thank you very much for your kind introduction. I will not talk about Costa Rica right now, so you don't hate me because it's nice and warm there. And if someone who knows how to dim the lights could help dim the lights, because I'm not quite sure how to do this. But the images that you saw scrolling on the screen are my, everything was taken by me. This is the kind of the upside of being an earth scientist and having an opportunity to travel. I just ran a slideshow of images taken in the line of duty. This is the actual talk. And unfortunately, I don't have a pointy device, so you'll have to make do with me flapping my arms. So unlike the previous speaker, the previous talk dealt with real hazard, a real danger to society and the Earth properties that lead to it and our attempts to understand them and to relate to them. I face a somewhat opposite, and I'll tell you a story which works slightly differently in the sense that I conducted a standard run-of-the-mill research project, and I got some results that I felt were interesting, and I published them, and I found myself in the middle of a bit of a media frenzy. It was 2 years ago, but if you go to Fox News site and look for my name, you'll get the link. It's still live. It's interesting that it just refuses to die. And this is where, ooh, wonderful. I get 20th century technology, laser pointers. Thank you. So I found myself facing this very unusual event where all of a sudden, what I did in my daily life, which I thought was perfectly obscure and academic and had nothing to do with human interest, became the source of all these headlines. They're all about me and my work. Now, my task today is to relate to you, like, both what I did, like what was the study, and also maybe you can help me come to grips with the fact that it somehow triggered this intense interest. So I think it's a story about the fact that on one level, well, I'll come back to this again, but the degree of interest was both gratifying and daunting. I got to tell you, nothing is more threatening and frightening than trying to talk about your science on live drive-by radio. When you have to assuage the perceived fears of a kind of a radio talk jock, the guy who speaks over the traffic in Massachusetts, and you just sit there and try to not to make a fool of yourself, and that was probably one of the most stressful things I've done in my life. So anyway, the study that we published had a perfectly boring title for most human beings: Seismic Evidence for a Recently Formed Mantle Upwelling Beneath New England. It had something to do with the interior structure of the Earth and the fact that we could measure how it moves. Before I go on, let me just acknowledge the fact that my co-authors here are Maureen Long, professor of geophysics at Yale University, and the more gratifying, the last three authors were undergraduate students at the time. It was their work, it was their results that they developed in the course of their research projects with myself and with Maureen that led to the formulation of the study and to the fact that we published it. And I felt extremely good that we could have them as co-authors, and without them, this study wouldn't happen. Now, the key point of the paper that came out in Geology 2 years ago was that we identified a hot blob, that's a technical term, beneath New England, and we were able to argue that it is a recent feature, and most importantly, we were able to prove, at least to the best of our ability and to the satisfaction of the reviewers that this thing is rising. Now, before I go on, here's the vocabulary word for the day, blob, courtesy of Pixar Animation, and this is the example of usage. But to be serious about it for a moment, how do you describe an object that is more round than it is long, doesn't have a defined shape? It's a mass that is somewhat roundish, doesn't have any kind of geometrical definition, and a blob seems to be like a good word, and it's stuck in all the titles, of course. I guess I used it a few times in interviews, and then it just went. So that will be the word I will refer to a lot. Before I talk about the actual study, let me do like a 5-slide Geology 101 lecture. So we live on an object that is roundish, it's a blob, and has a center made of iron and the outside made of rock. We are, of course, on the outside here. The center is very hot. The distance from where I'm standing to the center of the Earth is 6,375 kilometers, give or take. The temperature difference is very large. Most of the outer shell is made of just about 5 chemical elements: magnesium, iron, aluminum, silicon, and oxygen. Just like the rest of the rocky planets, by the way, Mars and Venus and Mercury, they all have the similar structure. Now, the question obviously comes up, well, how do you know you're standing on the outside? Well, that's my job. Most of the facts that we put in our introductory textbooks about the Earth, about the deep structure of the Earth's interior, come from observations of seismic waves. These are vibrations emitted by earthquakes. Okay, the talk given just before me dealt with the source of these vibrations, with earthquakes, with mechanisms, with reasons these vibrations would propagate. My take on Earth science is I use this energy as the source of information. Like an astronomer would use light or other electromagnetic radiation from outer space to study what's outside of the planet. I use these subtle vibrations. Sometimes they're not subtle, sometimes they drop a building, but most of the time when I work with them, they're subtle. I use them to probe the interior of the Earth. We can measure the time it takes vibrations, seismic waves to go through the Earth. We can look at their shapes. This particular poster assembled on the screen behind me is produced by IRIS Consortium from Northridge earthquake in California, and it represents records, these wiggly lines, they're called seismograms, all around the Earth at different distances from the source. So we can assemble this information, and over the last century or so, since the inception of instrumental recording of earthquakes, we are able to study the Earth by means of this phenomenon. And it's basically the light of geophysics. It's the thing that allows us to see. You would all recognize that rocks are very difficult to see through. Humans are not endowed with an ability to see through rock. And digging, how deep can a human dig on this planet? Any guesses? About 7 miles, I think I would say. 11 kilometers to the best of my knowledge, maybe 12. Now, compared to 6,300, that's not very much. For everything else, you need remote sensing. And of course, that gives us this layered structure that you see in any textbook. I see some children in this school, in the audience. They are probably the ones who have seen it recently. New Jersey teaches earth science in 6th grade and then forgets about it. So one of the things that I will focus on today is that the outer part of our planet is covered by a stiff shell. It's called the lithosphere. We define it not by chemistry, not by its chemical distinction, but largely by its stiffness. The fact that it is more strong than material beneath it, and it can sustain loads, and it can move. And plate tectonics is this ruling, currently governing paradigm that explains how the surface of our planet, here rendered as a rectangular map, with poles much expanded, is divided into sequence of areas that are termed tectonic plates. They're defined as areas that do not deform inside, but all the deformation, all the collisions, all the activity, all the geological processes are largely concentrated at the edges. That is the fundamental premise of plate tectonics. As an aside, of course, it's not completely right. There are exceptions, but for the purpose of today's talk, it will do. And so we live on this plate, North American plate, and that's the one I will be talking about. Here's just for those of you who have never seen those animations before, you can pull them off the web. They're quite cute. Here's the one making the Atlantic. So you're growing a tectonic plate here by volcanism, and you're removing unnecessary material behind on the other side of the globe by putting plates back into the Earth. That's how we think things work. And going back to Eastern North America, of course, it's in the middle of the plate. And the area we live in, and New England I will be talking about, is a so-called passive margin. What does it mean? Well, it means, first and foremost, and here's like my official statement, there are no volcanoes in New England. And there are no large earthquakes in New England most of the time. There was one in Cape Ann area in 1700s. So it is an area that last experienced any kind of volcanic activity 100 million years ago. Now, for a person who studies the entire planet over a course of its 4.5 billion years existence, 100 million years is not much. For most humans, it is an unfathomably large time interval. And the history of how this landmass on which we reside came about is written by its rocks, and here they're shown by different colors. I just marked them in very large kind of chunks. So the area that is red is over 2 billion years old. It's an amazing experience to stand on rock here. It is about half the age of the Earth old, and nothing has happened to it for half the duration of the planet's existence. It's been on the surface since then, and it sits there. The core is very stable. Then we have an area that was added about 1 billion years ago. The Appalachian Mountains in which we reside are about 0.3 billion years old, and the Atlantic opened, slightly less than 200 million years ago. And since then, nothing happened geologically. It is all supposed to be quiet. So as you can see, it's kind of an onion structure, older in the middle, a wraparound of younger and younger material. Looks like this. To make it more similar, I can twist it so that this is the core of the craton. This is the Appalachian Mountains, New Jersey. The obvious question that this brings up is, if this is the structure of our continent, as geologists who walk the surface will see it. You pick up rocks, you measure their age, you determine their affinity, you can make a map. What happens if I go a little deeper? What happens if I go 10 miles deep? What happens if I go 100 miles deep? Will it still have this onion structure inside? Like, is the entire continent that extends a couple hundred miles down made like an onion? Or like an ogre, for those of you who remember Shrek. Actually, no. That was the interesting thing for me. The result that we got from our study of deep structure of this area was that it doesn't seem to obey this simple expectation. It tells us something else, and that was scientifically very exciting. That led to a publication. Before I go to the actual publication, let me talk for a moment about what made this study possible. And this is supposed to be animated. Yes. You will see little triangles appear on this map. So this is a time history of an EarthScope project that took place between 2003 and 2015. And this is a largest single seismological experiment conducted at its time. Currently, there are larger experiments being done in China, but this was the inspiration. And it was one of those transformative ideas about how to do science. Not necessarily what science to do, but how to organize science. It was a nationally funded attempt to image an entire continent on a uniform grid with open data, meaning that every triangle would be a seismograph placed in some point. Basically, every census tract got a seismograph. The space between them was 75 kilometers, and they were rolled across the country by a crew of really large men in trucks. And given that there were 400 instruments in a grid, in an array, and it had to roll across the country, this crew of large men had and women, I suppose, had to pick up one instrument and drive it a few hundred miles every day for 10 years. Every day, because, just to move it. And the effect of this experiment, where you collected seismic wave observations over a uniform grid, over an entire continent, and made it available right away, within a minute of recording. It was sitting in a database where you could pull the data out. This was not normal. This was completely new, and that revolutionized the way geophysics can be done. It inspired other organizations and countries to do it this way. And I think it was compared to the Hubble. It was listed as, I guess, one of 100 most awesome or some other experiments done by man. But the way I think about it in terms of what it gave me as a scientist, if I were to turn the lights off in this room and use this laser pointer to find something, I will see things, but they will be tiny, and I will only see one at a time. And then I turn the light back on, and then I can see everything. That was the effect. All of a sudden, you could see the entire country, the entire continent, in one go, with uniform resolution, with consistent imaging. So it changed a lot. Some things we expected to see, and we saw them, and many more we didn't even think about when this project started, and when it ended. Now the world is not completely different. Instruments, they look kind of like this. This is a sensing device. There is a box of electronics. The ones used in the national project were slightly larger. This is my own project and my students burying a sensor in the middle of Quebec. But you bury this in the ground for 2 years, and you hope nobody steals it. This one only got vandalized once. And we come back and we read the memory, and then we use the data. And that gives us these basis to write papers like the one I published. Now, going back to the title, I have to talk about the hot blob in New England and show you that it's recent and it's rising. Now, the first challenge that I face here is I need to see through rock and construct images of the interior structure of the Earth. The tool for this is called tomography. It would be familiar to anyone who saw a baby sonogram or maybe a CAT scan of the head. Basically, it's a method of seeing inside a closed and a homogeneous body, an enclosed body, without cutting that body open. It's particularly good when it's about your head, but of course we cannot do this to the Earth. So what we do, we have earthquakes emit their seismic waves, we pick them up at different places, and we have some knowledge about the materials these rays go through, so we can anticipate how long it will take these waves to get to the different positions. When we see a difference, we can anticipate where the different properties should be, and using many, many observations, we can kind of map out the different properties inside the Earth. In this case, the property will be the speed. How fast does the seismic wave go? And that property is related to chemical and physical state, chemical properties and physical state of the material it goes through. So it's an imaging technique. And the first point I wanted to make is that if you wanted to find, like, how do you know that there is a slow, seismically slow blob inside the Earth underneath New England? All you really needed to do was look, basically construct an image. There are three different studies, and anyone who ever constructs this study with the new data from EarthScope finds this blob. Here's one from a study in 2014. There it is. Bright orange means it's slower. Blue means it's faster. Here's another one in study in 2016, and this one is also in 2016. They'll use different types of seismic waves, different mechanisms of different computer programs. These are different people. Everyone agrees this thing exists. Fine. So that point was not in contention. It's not even my work. I just knew about it, and it was a starting point for our study. Now, the second point that I would like to make is that it should be hot, and that requires a little bit of physics. So shear wave speed, the speed with which a wave that twists the material, and just, shear waves do this. They propagate from me to you while moving material like that. And this kind of wave has a speed that is directly proportional to the shear modulus and inversely proportional to density, like any other seismic wave. And if you make the material warmer, both of these coefficients change, but density changes more, and so the speed actually drops. Now, from a concentric circular diagram I showed you a couple of slides before, you would remember that if you go into the Earth, it's all made of more or less the same rock. So the logic here is that if you change some property and the material is the same, the only thing we can really play with is temperature. So we can anticipate things that are slower to be hotter and things that are faster. Where they're painted blue, the speed is higher, so it's colder, and where they're painted, in this case, kind of ugly green, I guess, you would say, well, this is much somewhat slow, somewhat warmer. Of course, if you go all the way to the west and underneath the west coast, where different tectonic processes are taking place, it's much slower and much hotter. But the scale is still, it's pretty warm. So we know that it's there, and we know that it's hot. And of course, while it's somewhat puzzling for the people who study the Earth on its long-term evolution, we think of the interior as being viscous. It's not solid, it can flow. Pretty much like glaciers would flow in response to gravity over time. And if you imagine a viscous material with different density in it, with things that are slower being hotter, so they are lighter, lighter things should rise, like in a lava lamp. Here you see another map of New England with my blob outlined in red. It is still the speed of seismic waves, so it is a proxy for temperature. This slice is taken at 195 kilometers depth, but so about 150 miles in. We would expect this to rise, but how do you know? I mean, one of the downsides of being a geophysicist is that seismic waves propagate through the Earth very quickly, and they only tell you what's there now, today, this minute. We cannot see yesterday, and we don't know about tomorrow. So there is no history in our observations. We need to somehow infer them. So it would be neat to have a way to see how the material of the rock that makes up our planet, whether or not it moves. It would be kind of convenient if we had an indicator for that. And lo and behold, we do. The Earth is made of this rock. It's mostly aluminum, magnesium, iron, aluminum, silicon, and oxygen. And no aluminum, sorry. It's called olivine. In its beautiful crystalline form, it looks like this. Maybe you can even walk across the hall after the lecture and buy some. This is not a plug. I don't know if they sell it, actually. But in its jewelry version, I think it's called peridot. And so this material makes up about 2/3 of the mass of the outer third of our planet. If you cut our planet in half and allowed it to cool, it would be green in color. This crystal has very interesting properties. Well, first of all, it is anisotropic, meaning that one direction through it is different in its properties from another direction. There are many materials like this in existence, or many objects. You can think of a book being anisotropic. You can open it only one way. Try opening it the other way. Ice is anisotropic. Traffic in New Jersey is very anisotropic. Coming here and going home on Monday, like if I forget my lunchbox on Monday, I live in Fort Lee, I cannot go back for it. I will never return. Now, the olivine crystal has 3 axes, and one is transmits elastic vibrations much faster than the 2 others. That's one thing to know. And the other thing to know is that if you push that crystal slowly, without breaking, it tends to realign its crystalline lattice. This is a general property of many solid materials. It's the creep that occurs on the crystalline lattice, so the entire lattice rearranges. But because it's anisotropic, So you get the change in which way the fastest direction is if you deform the material. So the logic of connection is that most of this part of our planet is made of that. It's anisotropic. We can go measure something. So the links that I will follow are that we can, if we can make one crystal change its crystalline lattice in response to some force, a polycrystal material, this is called the heart of stone. That's a mantle rock that we found about 15 years ago. It's a real shape. So if you squeeze this kind of rock, all of its crystals will realign themselves, and then we can make some seismological observation, and it will tell us which way they are deforming. So we can basically see slow deformation inside the planet by measuring something with seismic waves. And here's the logic. So we study this property called anisotropy. We map the rock texture from it, and we infer slow flow. And remember, I wanted to prove that my blob is rising, right? This is why I'm trying to do this. Now, the method that I will use relies on a particular seismological observation, which is very similar to optical birefringence. I presume this should be familiar. There are materials that you look through and you see double. In this particular case, you see an example on the screen. It's a crystal of so-called Iceland spar, but I believe some other materials have this property as well. In animation, what happens, a seismic wave that is polarized transversely, so if it goes this way, it oscillates that way. In an isotropic material, it's just oscillating like that. If it finds an isotropic material with different speeds and different directions, it splits. And you get two instead of one. It's a fairly simple observation to make. If you put a seismograph into the ground, an earthquake happens halfway around the Earth, you measure a particular kind of wave, you record it on a seismogram, you expect to see one pulse and you get two, it tells you that you have some anisotropy in the Earth, and you can try interpreting it. And I will not, bring up all the technology through it. I hope you will either believe me or pester me with questions afterwards about how exactly that gets done. But what you can do with it is you can make maps that look a little bit like a field of grass. And what they say is that at every location where there is a little gray stick on the map, there was a seismic station, and it collected a number of these observations, and they all agreed that the fast direction of propagation is along the stick, and the size of the stick tells me how strong the effect is, how much the two waves will separate, meaning whether the strength of this property that I want to see is large or small. And remember, these lines, they should be pointing in the direction where the rock is being deformed, so they are more or less our shearing or deformation in the Earth, and I want to study that to see if my mass of rock is rising or not. But the first view that I get here is that they're a little scattered, but mostly things are aligned east-west, northeast, southwest, and this is the direction in which the plate, the North American tectonic plate, rides over the rest of the Earth. So that's not a big surprise. You have something stiff, it moves over something somewhat more gooey inside the Earth. The difference in that, the bottom of the plate will create this band of shear, and you would be mapping it. So that was not a very dramatic result, except for one thing. It was not uniform. And a couple of places, if we look closer, like zoom in, there were places where you just couldn't measure this effect, even though we tried. And one of the advantages of having this EarthScope project was that all data were collected in a fairly uniform way. So there was no question that we're taking apples and comparing them to artichokes. We're taking the same observation most of the time and trying to make it very systematically. And by we, I extend it. It's the students. It's the undergrads. It's the people who actually do the work. Professors, they get to stand here and talk. So the measurement was done by the same human beings with the same technology, same computer program. It all worked the same way, except that they couldn't measure it in a few places. And one of those places caught our eye because it's right in the middle, like this one and that one. They're right in the middle of the red blob. Interesting. Why? Why would it disrupt the pattern? I think I have animation there. So before we got excited about this too much, I thought it would be prudent to test this in ways that would verify. You know, many of you remember the trust but verify concept that came from well, anyway. But yes, that's very important in science. And so what was done first? There was an earthquake in 2015 that was not included in the effort to make this map. So it was observed very well, and the analysis was performed in a very uniform, systematic manner. And lo and behold, in an area where the previous effort couldn't find this birefringence, this measurement didn't work either. So it was kind of an immediate confirmation. Very good kind of scientific hygiene, if you will. You have an observation, and you try to verify it by taking data that are unrelated to the original observation, doing the same thing over by different people, and so it all worked out. That was good. Then but of course you try and try again, remember? So then we tried to do this with just collecting a lot of data for all these locations and trying to average them to see maybe this was a fluke, maybe this one earthquake did represent things well. It still agreed that in the center of an area that we think is very slow at depth, the red one, there seems to be a few locations where we just cannot measure this birefringence that we need. So once again, the plate is moving, it's shearing the material beneath it everywhere, and you can see it well, except here. And we're certain we cannot see it there. Why? How does this happen? We need something special to explain it, because otherwise, you know, if you have the same rules but they give you different answers, that's kind of puzzling. So we were convinced that this is an observation. And let me just put it together into a little slide. So if the sticks on the map are attempts to measure birefringence, and they represent flow or deformation in the upper mantle shown by floating arrows. The smallest arrows, the weakest birefringence, is right in the middle of this red area. So the blob that we think is warm, it's also, has the, I think I ran ahead of myself. So this area has the weakest effect. Now you need an explanation. Once you confirm that this is an observed feature, we need some kind of an explanation. And this is where it gets a little geeky and technical, but the effect that I'm measuring only works if my crystal of Levin stands just so. If the class direction is horizontal, it's easy to see birefringence. If I flip it on the side and point the axis vertically, you don't see it. It's almost like, well, I'm not quite sure what analogy to give you without blinding myself with a laser pointer. So basically, if we allow the deformed rock to have texture that is vertical, either up or down, we will not see the effect that I've been trying to measure. You know, it's proof by negation, but this is what got me and my colleague, Professor Long, initially so excited. So we had our undergraduate helpers and assistants try again to measure this again, and they still couldn't. And then we got convinced that, yes, indeed, we have this effect. The most plausible explanation for our inability to see the feature that we wanted is that all of our mantle rock is sheared in a vertical direction. Mind you, we cannot prove whether it's going up or down, but given that it's warm, it's more likely that it goes up than it goes down. And so to summarize this, it's something like this. We have evidence for something that's hot, and we see this weak birefringence, so it's good evidence for it to be rising. And that was more or less the sum total of what we wanted to publish, that we see this volume, it sits underneath New England, it's hot, and it's rising. Now, these two words were probably a little bit too exciting. That led to the media frenzy later, but in the meantime, before I get back to that, let me just, first of all, emphatically state that there are no volcanoes in New England. There were no volcanoes in New England for a long time, and unlike many other things, as a scientist, I'm absolutely confident that in my lifetime, in everybody else's lifetime, probably in the lifetime of our civilization, there will be no volcanoes in New England. Not right now. It's just not possible, given everything else we know, unless we humans develop some technological means of doing it. But that brings up the question, well, how old is this thing? Because remember, my title also said it's recent. And the argument for its age being less than 50 million years is a little bit involved. I'll be happy to discuss it afterwards, but basically it's too small. If it is this small and still hot, it cannot be old enough, otherwise it will cool off and equilibrate with the rest of the planet. It will not be as, you will not be able to see it if it's older than 50 million years. That's more or less the sum total of the argument, that you make it by doing computer simulations. Much more interesting question is, why don't we have volcanoes in New England? Why don't we have any surface expression? If I measure the force of gravity, if I look at anything else, magnetic properties, or there are no earthquakes concentrated above it. Like, why is there no surface expression of something that is clearly very different inside the Earth? And there are two possible explanations. One is very boring. It's too small. We have 100 miles of rock above it, and it is just too small to be felt through it. I mean, usually, unfortunately, in science, very often, the boring answer is right. It's good to get an exciting one, but I stress to my graduate students, including those sitting in the back of the room, that a boring answer is often the one you have to expect, and you have to brace yourself for it. There is a much more interesting answer that, it intrigues me, and at the moment I don't have any means to prove it, but it's an intriguing thing to think about. If this thing is really new, it is formed not 50 million years ago, but let's say 5, and it just didn't have its effects felt, well, then there will be volcanoes in New England. It's just, we have to come back in 10 million years, maybe 15. Let's all work on time machines, right? Or go into some cryogenic sleep. But that is a much more interesting possibility, and honestly, at the moment, I don't really know how to probe it, but it's fascinating to ponder. Now, why is this interesting? Why did I devote so much time to this, and why did I do this work? Well, let me go back to the premise, the original premise. Eastern North America is a passive margin. For all we know, it has no volcanoes, no deep earthquakes. A last significant episode of tectonic activity took place 100 million years ago. So what we see in deep mantle beneath it is not supposed to happen. This is the deviation from that onion structure. Like, there's no particular reason for this thing to exist in everything that we see on the surface. We cannot explain the presence of this feature by what we know and what we teach in our textbooks. So this basically requires new science. We have to think differently. We have to come up with ideas. The paper that we published had one particular idea. I can chat about this, but let me just finish the arc of the argument here. But I'm not sure the idea we proposed is right. What I want to stress to this audience is that this is how science, I think this was extremely gratifying, because this is how science is supposed to work. You find something technical, and once you put it into a framework of a big picture, you see, oh wait, it doesn't match. And there is no particular reason for this to be, but you still have it. You're convinced that it exists. So this is where you go, okay, well, I guess I write a new proposal. This is how you get funded, or how you... But more to the point, this is what makes my life as a professor of geophysics interesting. It doesn't happen very often. Most of the time you get the boring results that you expected and you see the details, but every so often life smiles, and I cannot tell you just how pleasant it was when we looked at this map and I thought, well, we have a hunch it might work. And then students came back with data and we're like, my God, it really does work. This is one of those flashes of gratification that scientists get I don't know, once every 5 years? I don't know. Hopefully more often. So I presented the evidence to you that there is a hot blob beneath New England, that it's recent, and that it's rising. Hopefully it was reasonably convincing. And we have a publication here at Rutgers, Rutgers Today. It has a very creative and capable writer, Todd Bates, to whom I deeply bow. And he came to my office and we chatted for an hour and he did a press release, and I thought that's what will be the end of it. And then, of course, this happened. And I guess these were the two words, the hot and the rising, and New England. And I don't quite understand why. And I spent so much time explaining the concept of upwelling. That word, which is so natural for anyone who studies anything like about the earth or the ocean, or those who sit on the Jersey Shore and hear on the radio, the coastal upwelling, you cannot swim, it's too cold. We all know what an upwelling is. What is an upwelling? But yeah, I mean, it got mistranslated into Russian. It was reported in Spanish, and I don't know. I don't read other languages. So one of the most amusing examples was sent to me by a student more recently. This is from a sports bar in New England, in Long Beach Island. Now, you know, consider the meta sense of this. Like, my name is being used to bash New England Patriots. Now, I have to be extremely careful about it because my colleague, Professor Long of Yale, she's a Boston girl. She drinks Dunkin' Donuts coffee and roots for the Pats. I'm not showing this to her. So, you know, that's what I wanted to show you. I mean, I did the study of the Earth. It was interesting, it was pleasant, we published it. But having it in the public eye yielded this absolutely fascinating experience. It continues. I still get emails every so often from people whose house is creaking because there is a upwelling in the mantle, and there are volcanic things. And let me finish this by saying that the new science that I told you we need, we're doing it. So my colleague and I scraped together a little bit of money, and we're trying to deploy a line of instruments across our hot blob, but at much smaller spacing, so we can actually see more detail and maybe understand it better, because there are certain things we don't quite fathom. Like, it's not uniform. It clearly has patches of different properties. And this is us. Well, I'm taking the picture. These are my graduate students, her graduate students, and Maureen Long in October of 2019. So just a few months ago on a garlic farm someplace in New Hampshire, maybe Maine, just on the border there. Anyone has a country house, farm, uncle, like chicken coop there? Because this is one place where we don't have a location. We were trying to place our instruments in a uniform grid about 20 kilometers apart. And we found most of the locations that are marked on the map, and the purple ones are already working, and the green ones are just set up, and then the yellow ones are promised, but it rained too hard and we couldn't do it. And then we need one here. So anyhow, with this, I thank you for your attention, and I'll stop here.
Thank you. We have time for some questions. Yeah.
So you have an example in New England because of this big seismic array that was put out. It seems to me the one interesting question is, there are other places in the world where such a thing is occurring that you could compare this to?
Yes, of course, it's both a good question. It has partial answer in the same images. I can, let me not go back to them, but along the eastern side of the North American continent, we count about 4 features like this. And the one in New England seems to be the most prominent. There is one beneath Virginia, there is one kind of on the border of Florida, northern Florida, and there is one towards the Gulf of Mexico. So they seem to be positioned themselves along the eastern edge, which is the old orogenic belt. You know, when continents of North America and Africa were together, this was the mountain range between them. Areas west are older and thicker. So we do see 4 features like that, and indeed They all deserve study, and that will be the focus. More strategically, yes, in the next 2 months, I'm supposed to write a proposal with a colleague at Columbia to study the other continents and see. The catch is you need high lateral sampling. With the seismic wave imaging, you can only see objects that are as big as the distance between two instruments. This is why in New England right now, we're placing our instruments at 20 kilometers. We want to see smaller things. That takes money, that takes effort. So yeah, I hope to see that. Actually, these are two possible outcomes, and both are interesting scientifically. If this only happens in North America, it is something special about our particular continent. If this can be found in other continents, it changes the rules of how the planet works. So both are interesting. You know, either there are different rules for different continents, that would be interesting. If there is just a different set of rules, we don't anticipate them yet, that's exciting too. Yeah.
I mean, I don't know how this relates exactly, but the speculation about the Adirondack Mountains in New York, which are a dome-shaped bunch as opposed to the ridge-like Appalachians, and that they have been rising, and that's why a lot of earthquake activity was originally studied up there. There's a good number of quakes. Okay, maybe glacial rebound, but some have speculated maybe there was a warm spot under there, and if you move the continent west, it will move under New England. Is anything related to that, or is this totally crazy?
This definitely comes up in every conversation I have about this work. The Adirondack Mountains of New York, upstate New York, are a roundish in map area, mountain range. It is much older than the Appalachians. It's 1 billion years old. What we understand about it, it was like the Tibetan Plateau, twice as high and thick as the most other mountains. Currently, if you walk on them, you find rocks that were baked at 20 kilometers in the earth, 15 miles in the earth. Currently, they are lining the surface. So you stripped away the top 15, you still have about 40 kilometers of crust left. So it's possible. Whether or not they are rising now is an interesting scientific debate for which I don't have a good answer. Because I've heard arguments for, I've heard arguments against. There's a recent study out of Amherst College that proposes some kind of a warmer feature beneath them that would prop up the Adirondacks themselves. How to put it politely? It's one study, and I'd like to see a few more before I completely buy into that idea. But yeah, this is a very obvious question. Whether, things that are at depth can be linked to the surface. Of course, they are separated in space. The plate, maybe. It's definitely something that would be a part of the thinking process as you write more papers. And it would, more to the point, it would guide the future data collection and analysis. Like trying to understand what would I measure to answer this question is what my job is like. This is what I have to do. But thanks, yeah, that definitely is something to think about. Oh, yeah.
Now for something totally different.
Absolutely.
So you mentioned a little bit about my background in psychology and sociology. So you've talked about why you had this reaction. And I think part of it might be the sort of political milieu and what people were thinking about at the time, and the use of the word blob also. Because there's this whole imagery going back to the 50s of the blob, this amorphous threat.
That's the thing. So just to restate the question for the rest of the audience or the comment, that the word blob triggers people in New England in ways that are distinct and unique to them. Am I rendering it right?
Yes. And also I was going to say that may go back to, some people would argue they're real, but there was a sort of heyday of UFO spottings when folks were worried about the Cold War. So they're saying that somebody might have projected their fears onto your research.
I don't think I've gotten a fearful response, as a matter of fact. What was gratifying was that I think the response was more, it revealed the deep-seated interest and the desire on the part of mass media. I mean, like, you are looking at a living, breathing clickbait That's how I figured out it was. You know, you put a title like this in a news source on a slow day, and people just click it. So I'm clickbait, and you know, to be fair, I'm vain like everybody else. I like it. But on some level, I'm happy to see this being clickbait and not other stuff. You know, I'm perfectly happy to interact and to explain that no, it's, you know, the title is over the top, but the description is better. I think it was fascinating just how much response came back from, in particular, readers of the Fair and Balanced source of news. Those are the most active readers. They wrote the most email. It was amazing. And some of it is really out there, but some of it is quite interesting. So I think it was generally a positive experience seeing that scientific results trigger this kind of response. I had to deal with a number of inquiries about how do you feel about misrepresentation of your work in the media. Those came out of news sources that specialize in debunking and correcting the record and all that. And my response, frankly, is my ego is boosted by that. You know, yes, some of this is ridiculous, but it's better to talk about science than to talk about, you know, well, you know who. Yes?
I suppose you're not saying that this hot block came from all the way from the core mantle boundary. If it didn't, then what would be the origin of it?
Okay, the question is, where does this thing come from, and does it have roots deeper into the earth? Let me address the second part first. Definitely not, because the imagery that we have is good enough to exclude the extension down. It is concentrated between about 100 miles and 300 miles. It is very localized, so there is no, like if you go under Hawaii, there is a thread all the way, the stem that goes all the way down to the iron core. But this one doesn't have it. The model for it is, let me spend just 1 minute trying to spin it into a quick explanation. It's kind of a localized little swirl in the body of the planet, and the way you would explain it, imagine an ice cube stuck into hot coffee. Coffee right next to the ice cube will get colder and will start flowing down. When it does, it will push hot coffee back up. So that's the model, if you will. The central part of the continent, not the Patriots, here. The central part of the continent is very old and very cold. And it's cooling material around it and forcing it to go down. And every so often, the swirl might come back. The question is, why does it happen in some places and not others? And I don't have an answer. So yeah, it's fascinating. It definitely doesn't go deep down. It's localized. And that really goes back to, like, this is not supposed to happen, but it does. Good enough? Yes?
Does this have anything to do with a number of years ago in New Hampshire, the old man of the mountain fell down one winter?
You're tempting me to give a very facetious answer. But of course, the serious answer will be no. Of course not. We all cry for the old man on the mountain. I dearly love driving through Franconia and seeing him. And I presume it was a he. No, but no, I believe actually the demise of the glaciers and the eventual, erosion of the rocks that were exposed after the glaciation has the most to do with it. As I said, I mean, this feature in the upper mantle, which is 190 kilometers in this slice, has no visible impression at the surface right now, which is a puzzle that, I'll work on next. Yes?
You said, the Earth scope is in the U.S. Is it on other continents? You said you wanted to look at other continents?
Well, yes, the EarthScope program was authorized by Congress and was embedded as a line item in President's budget for 10 years. It continues in Alaska right now. The last year, the instruments are being pulled out from Alaska. It ran at the relatively modest cost of about $50 million a year. And, it did its job and it's done. You have $50 million, I'll deploy this array somewhere else. Currently, China has arrays that are twice the size, 800 nodes, and they're moving them around. Europe has something called AlpArray, I think, or something like this. This mode of doing stuff, mode of doing science, was transformative 15 years ago when I was just coming out of grad school. And, well, no, I was not already, sorry. But the most important thing about that effort was not so much its scale, but the willingness to open the data to all at once. We completely overloaded the Cisco systems because they said, oh yeah, your bandwidth, the amount of data you want to transmit, no problem. We'll give you a few satellite links and you'll be doing it. They choked. But yeah, it was an interesting development, a very important development in the way we acquire knowledge as a society. That, a very standard mode is I sit in my lab, I measure something, I work on it for 10 years, I publish. This is not that. All data went out, anyone with any ability to process these data could work on them, and it changed the rate at which you had to work. And it also, 2 brains are better than 1, 200, scaled up. Yes? So, yeah.
It interests me that these hot blobs are oriented down the Atlantic coast.
Like this? Yes.
Yeah, okay. As we have seafloor spreading, forcing both sides of the Atlantic apart. From what I've read, eventually that is going to stop. The continents will stop spreading apart.
They have to.
And the reverse will start to happen. You're going to start getting subduction zones along both sides of the Atlantic, and it's going to begin to close. What would the very earliest phases of the beginning of a subduction zone look like?
That's a good question. It's actually one of the unanswered questions in our current science. If you, what image should I use? Just this one is good enough. So this is the ocean, this is the continent. This material was made by volcanic eruptions underwater. And at some point, we know from the geology history of this continent, these ribbons of different rock were formed when 2 continents collided, then ripped apart, collided, then ripped apart. This is known as a Wilson cycle, proposed by Tuzo Wilson in the 60s. It's being challenged right now because it seems to only work here. It doesn't really apply to California, for instance. It doesn't seem to explain what you see in Alaska. So in the past 1.5 billion years, this part of the world did exactly as I just described. The principle of uniformitarianism that we teach to our students in undergraduate classes implies that it should do this again. One wrinkle in all of that is that at the moment, we don't have a good physical model that would allow the lithosphere to break along this line. For all we know, once it cools off and it becomes very old, it's too strong to break. And so far, and I just happened to have taught a class about this a couple of months ago, we know that this has to happen somehow, and we really don't know how it initiates. Makes my job fascinating.
Another question or two?
Do you have a prediction of what the blob will do over time?
Well, assuming I'm right, which is always pleasant, and it's going up, right? So it's the question of whether it's hot enough and how to measure its temperature is a separate paper to burn through or move up. If it's really warm, it might actually burn its way through, but more likely it will. Right now it seems to sit about 150 kilometers below the surface. Whether the balance of force between its buoyancy and the stiffness of the overlying material will allow it to move further up, or will it just sit there? I'm not sure I can answer that. there's a fascinating wrinkle in this that I'm discussing with my colleagues, is that it's not the first time you had something volcanic, potentially volcanic, happen there. White Mountains are volcanic in origin. It's right beneath them, and they are 100 million years old. So we can run. There are people who study the Earth by computer models, and you can definitely make predictions. They typically have 1 or 2 numbers in them that are completely unknown. Like, what is the stiffness of the Earth's material in that place? And you can take a range, and depending on which side of the range you will end up, it will either get sheared by the, plate will move off and make it into like a smudge, or maybe it will just burn its way through, and then the Patriots are really cooked. Yeah.
Can you assume that as it goes up, it cools down and everything slows down until it stops?
Well, I mean, then it will just integrate itself into the body of the continent. And, the fact that we see it means that it's different. Once it cools off, we cannot see it. That's the thing. And so then we don't know it's there. So if the blob cools off in the mantle, do we know it? It's like the tree in the forest. Do we have, I mean, I can keep talking, but...
Maybe those of you who have questions, Vadim, you'd be happy to speak with them individually. And please join me in thanking Dr. Levin again.
Thank you very much.